already have on stage with me Alexandru Căciulescu, Senior Software Engineer at UiPath. He has a very varied background, and I know that many of you have been waiting for this talk. So without further ado, let's talk about fuzzing the stack for fun and profit.
Thank you.
Give a big welcome to Alex.
Thank you, everyone, and welcome to Fuzz the Stack for Fun and Profit. I know it's the second day, it's late, you've made it so far, keep going. So first of all, we've seen Jeff's presentation early today. Can anyone notice where I stole the title theme from? Anyone? Okay, so maybe it's really an old article called Smashing the Stack for Fun and Profit, so that's the inspiration for the name. It's a really cool article. It's basically about buffer overflow, so if anybody's interested, shout out to that, give it a try. So, who am I? I'm a security enthusiast, open source supporter and contributor, and currently a senior software engineer at UiPath. And hopefully some of you will recognize the last reference there. Exactly. My contact, if anyone is interested. Now, all right. I know it's late for most of you. You might be hungry already, but let's do this. And after that, we can go back to drinking beers and killing our brain cells. So, after this talk, I want each and every one of you to learn 3 simple things. What is fuzzing? Why is it important? And how it works. And for that, we'll learn the types of fuzzing and the state of the art, the current limitations on the state of the art, and how we can overcome this with the new tool we're going to introduce today. So, what is fuzzing? From Wikipedia, fuzzing is an automated software testing technique that involves providing invalid or unexpected data as an input to a computer program. The program is then monitored for its behavior, and we can see if anything like crashes, memory leaks, or exceptions happen from that said input. Okay, maybe it's a bit too formal. Let's try and visualize this. So basically what happens, you generate an input, which you feed it to the target program, and then you monitor the behavior. This goes on basically in an infinite loop until you detect some interesting behavior. And that behavior, you can probably generate a crash or a security exploit, and you can either use it for a defensive purpose, to patch it, or for an attack purpose, to see what you can get out of it. So that's basically fuzzing in a nutshell, from a high point of view. Now, before, the #1 programmer excuse for legitimately slacking off was compiling. Nowadays, people can use fuzzing for the same excuse. And I really encourage this. After you do your fuzzing setup, you can just run all of your cores, let it fuzz for 24 hours or even more, and just have a valid reason to just slack off. Now, why is this important? Well, first of all, fixing a bug at the deployment stage it can be more than 100 times more costly than fixing it at the development stage. Also, just to give you an idea, over 70% of the security vulnerabilities patched by Microsoft in 2006 were found by fuzzing. And also there's a thing called SDL, the Microsoft Security Development Lifecycle, where and this is basically the security Bible for the MS teams, and this states that fuzzing is a mandatory step in their lifecycle. How it works. So let's get a bit into the actual technical details. You may assume it's something black magic and it just somehow generates the magic input without any knowledge whatsoever. Actually, it's all quite easy to understand, and let's get into it. First of all, let's define the types of fuzzing. So you can define it into 3 categories based on the following. How it generates the inputs that it actually gives to the target. So based on this, it can be either generation-based or mutation-based. Generation-based means that you generate the inputs from scratch, while on a mutation-based fuzzer, you start with a pool of inputs, also called seeds, and you mutate them each round to generate new seeds for the target. The second category can be either white box, gray box, or black box. I'm certain most of you know what the black box means. Basically, you have no prior knowledge of the target. It's a complete black box. You can just give it something, an input, and monitor its output. You have no knowledge of what's happening inside of it. So that's a black box approach. On the other hand, you have the white box, where you have full knowledge of it. You know the code, the behavior, everything. And then there's something in the middle called Greybox. You know something, but not all of it. And we'll focus on this later on, more later on. And the last but not least category, a fuzzer can be dumb or smart. And this basically means if it takes into account the structure of the program input. So if it takes into account the grammar of the inputs, it's a smart fuzzer. If it takes nothing into account, and it just, for example, randomly flips bytes, it's a dumb fuzzer. Now, the current state of the art can be categorized as the following. It's a mutation-based fuzzer with a Greybox approach, but it's quite dumb. It takes, takes nothing into account about the structure of the inputs. And the current state of the art is the AFL fuzzer, the American Fuzz Lab. Hopefully, most of you are familiar with it since you're at DefCamp. And this is how it actually looks in the CLI. Now, why is it so successful? There are a few reasons for it. First of all, it runs out of the box. It's easy to deploy and configure, and it's fast. It's open source, and I have to emphasize this, it's really fast. Now, let me put it like this. The first rule of Fuzz Club must be fast. Second rule of Fuzz Club, it has to be fast. Why is this so important? Well, think of it like this. If you're a company that wants to automatically test software, and each time it runs a test, it takes, for example, 5 minutes. To actually get an interesting result, sometimes you have to run thousands, if not millions of tests. So that accumulates to a large amount of time. So the faster it is, the better, and less resources you use for it. Now, AFL has an impressive trophy case. It has more than hundreds of bugs, if not thousands. I couldn't actually find the list to summarize all of them like an exact number, but the full list can be found here at this link. And it includes tons of high-value targets, such as OpenSSL, OpenSSH, and even FFmpeg. And I encourage you to check the full list and see if, for example, a software you're using has vulnerabilities that have been found with AFL. Now, let's learn from our mistakes. For example, most of you are probably familiar with Heartbleed, one of the most notorious bugs that have been found in recent history. And, for example, there's an interesting blog post about it that I've linked in my presentation that actually talks and presents Heartbleed and how it could have been found if someone actually used the fuzzer on OpenSSL before releasing it. And within, let's say, a couple of hours of actually configuring everything, AFL is able to find and pinpoint the problem in less than 24 hours of fuzzing OpenSSL. So that would have been a huge win if someone actually took the time and fuzzed OpenSSL before launching it in that state. Now, how is it so fast? Well, it's a coverage-guided fuzzing, and I'll explain more on that in a minute, and it uses lightweight instrumentation for that. So this is the Greybox I was talking about earlier. So you might or might not have access to the full program, but you obviously have the binary to fuzz it, right? So what AFL does, it adds lightweight instrumentation to the binary and such that it gathers code coverage from each execution. Now, let's see how the coverage measurement actually works. What's the magic behind it? So imagine when you have an if, when it branches, right? For each if, you basically create a code branch in your execution path, and sequential ifs and so on. Basically, each of these branching represents a path in your execution tree. What AFL does for each of these points of branching, it introduces lightweight instrumentation which can actually be presented in these 3 simple lines of code. We'll not go into further details about this, but this is all the lightweight instrumentation it does. And based on this, it can actually measure each time you hit a new execution path in your execution. And that's quite important because you want to be able to measure the paths, the inputs that are actually interesting based on the new path execution. Now, let's look at the actual architecture of AFL. As you can see, we have the initial seed corpus here, the mutation operators, which actually mutate the inputs over and over for each iteration. Then it feeds the input to your target binary, which has the instrumentation added to it. Based on this instrumentation, the fuzzer is then obtains code coverage and takes into, based on this, it evaluates the inputs. And then this goes on in an infinite loop, generating more and more inputs. which are fed to the fuzzer in order to generate interesting behavior. And this is how you actually find crashes. Now, what are the limitations, the shortcomings in AFL in its current state? And to best show this, we can actually take a quote from the actual creator of AFL, and it goes something like this. One of the most significant limitations of AFL fuzz is that its mutation engine is syntax blind and optimized for compact data formats. Any general-purpose fuzzers will have a harder time dealing with more verbose dialects, such as SQL or HTTP. You can improve your odds in a variety of ways, and the results can be surprisingly good, but ultimately, it's never easy to get from set cookie foo equal bar to content length -1 but by randomly flipping bits. So that's the major issue with AFL nowadays, and with most fuzzers that are quite fast. They're dumb, they're completely unaware of the input structure, and they just do more or less bit flipping on the inputs in order to generate new input seeds. Now, how do we overcome this? What's the solution? We introduced smart Greybox fuzzing. There's a new paper and tool that has been published. I encourage you to go and read the paper if you want on the link, and also you can find the tool fully implemented and published on GitHub. So, what's new? What do we add to AFL in order to make it better? We add a virtual structure, smart mutation operators, and a validity-based power schedule. So let's talk about each of them. The virtual structure, think of it as a tree. So instead of AFL just operating on a bit level for mutating the seeds, now we operate on a chunk level in such a way that we can presume validity of the input seeds. The second addition are the smart mutation operators. So instead of just doing random bit flips, we now operate on the chunk level of the input seeds. This again maintains validity and adds a lot more flexibility in what we can generate. And last but not least is the power-based schedule based on the validity. So how does the AFLSmart architecture schema look like? As you can see probably on the left side, you can recognize the older schema right here, basically the infinite loop with the seed generation, mutation, and feedback loop. But now we also add the structure validity into the equation. Let's present a little bit the virtual structure. So in order for the new tool to work, what the user has to do, you actually have to define manually a virtual structure in the form of an XML file. This can take from tens of minutes or 40 minutes to a couple of hours. And this actually has a huge impact on the end result. The more time you take and the more granularly you define your grammar, the better the chances for your configuration to find interesting behaviors and new crashes. This is the only extra overhead you have as opposed to AFL, which just runs out of the box. The second addition, the smart mutation operators. So you have smart addition, smart deletion, and smart splicing, which operate on a chunk level now. So let's take the smart addition. As you can see, we have two seeds, S1 and S2, and a new seed which we actually have constructed from the two older seeds in such a way that we take valid chunks from each of them and we add them together in a way that we maintain the validity of the input seed. So this is the smart addition. After that, we have the smart deletion, where we can just delete a chunk in the same manner based on validity. And then the smart splicing, where we can actually find chunks of the same type and replace them from one input seed to another. Now, this may seem quite like, okay, trivial idea, but it has a huge impact on the end result. And now, last but not least, the validity-based power scheduler. So until now, how AFL worked, the validity is basically would be a binary function. It's either valid or not. Instead, we proposed a gradual validity function where you have a percentage on how valid the actual input seed is. And how this works, basically it implements gradient descent. And if the validity of the input seed is more than 50% and the initial power attributed by AFL is less than the total amount, we double it. If the validity is less than 50%, we maintain the old AFL power scheduler. Otherwise, we gave it the maximum value. Now, what we obtained with AFLSmart. We have more than 42 0 days attributed to this tool, 22 CVEs and counting, in high value targets. One of them being FFmpeg. And you can see here 7 CVs, which have been currently attributed, 3 of them of high severity, which are heap buffer overflows, heap buffer overreads, and a heap buffer override. And these can lead to some potentially serious attacks. Now, if you got a taste for fuzzing, I actually encourage you to go to the next presentation on one of my former colleagues and friends, Radu, and he'll actually present a more hands-on approach on how we can use tools like these for a concrete example of a fuzzing test. And I encourage each and every one of you to try AFLSmart yourself. Thank you. Questions?
Yes, we have time for quite a few questions, so let's start anywhere. Let's start here. Okay. We'll get to you, promise.
Hello, thank you for the presentation. My question is, so you improve the fuzzing algorithm by working at chunk level, not bit level.
Correct.
And implement some logic in, let's say, it's not so random, but how can you determine if the chunk is valid or not? How do you build a set of chunks, of valid chunks?
Okay, so first of all, someone has to manually look up the grammar and understand it. You define the XML tree, and then we use a third-party tool called Peach, which actually has inside it a tool that can actually measure the validity based on your grammar definition. And this is how we actually determine the validity. So basically, how big of a percentage it can validly parse of the chunk.
Okay, so for example, if I want to test a HTTP service, I have to choose words from the HTTP, I don't know, header or something like that.
Well, yeah, for example, if you can parse, let's say, just the header, or like, if you can parse, if you, for example, the target are the headers, and it can parse only, let's say, a few words or a few lines from it, which represent 20% of the full chunk, then it's 20% valid.
Okay, thank you.
Cool. Next question. I'll pass it to the gentleman on, yes.
Hi, nice presentation. I was curious as to what the impact is of making the AFLSmart.
What do you mean by impact?
Compared to the dumb version.
What the impact is?
Yeah, on the running times.
So running times are quite significantly faster. For example, for FFmpeg, if you have how you can measure the how good it is basically on the number of paths it discovers in a certain amount of time. So for example, for FFmpeg, which is quite a heavy-duty library, if it had, for example, X amount of paths, with AFLSmart we can actually obtain almost 3 times as many paths in the same amount of time.
That's cool. Thank you.
I encourage you to read the paper for the actual full...
yeah, I was going to.
Cool. Let's take a question from the other side. We'll get to you in the back as well.
Yeah, nice presentation. I got a question. So, how much grammars you are supporting with the tool? Is it easy to add a new one, or it's hard? And how is it going to happen?
So right now, I think there are about 10 or so grammars for like PNGs and whatnot, the most common formats, like WAV formats. So there are about 10 of them already available on the GitHub repo. And then it depends on what kind of grammar you want to add. So if you want to add something quite simple, it can take for example, a couple of hours. If you want to add a grammar quite complex, such as a PDF, it can take maybe days. It depends on you. But the main advantage is that once you design and implement the grammar file, you can use it for any fuzzing campaign. And you can, basically, if someone does it, they can share it with everyone. So it's only a one-time cost.
Cool. Thank you. I know we have a question in the back there.
Hello. I I have a question. Given the emergence of
Please stand up. Sorry to interrupt. Please stand up so we can see. Okay, thank you.
given the emergence of the DOSing as a service and generally attacking as a service, how much of a risk would you say is fuzzing as a service against unknown targets?
Fuzzing as a service. I'd say it's quite far in the future because let's say it's a bit of an art to actually set up the configuration. Each target is different. You need to, for a lot of targets, you may need to create additional scaffolding to actually help you attack specific parts of that target. So it's not as easy as it sounds for to create a service out of it. For simple things that just parse a specific file, like PNGs, yeah, you could have it as a service. But if you want to fuzz a protocol that has a complex grammar, it can be quite difficult and it's hard to provide a service out of the box for it. You have to tailor it to your specific needs.
And would it be able to tailor a fuzzer to attack a certain protocol, but would that fuzzer be portable to various types of applications using that protocol?
Well, yeah, to a certain degree. So, for example, an analogy would be, let's take pen testing. So, pen testing as a service, you have a lot of tools that can find low-hanging fruits, but there's not one tool that can find high-severity bugs quite easily. You need a pen tester to go manually in there and try different things to find the bug. So, it's kind of the same way.
Okay, thank you.
Cool. 2 more questions. Who's up for it? We have one over here.
Thanks for the presentation. The question is, does AFLSmart support hierarchical formats? So if you've written the grammar or the XML for HTTP and you also have one for MIME, can you reference the MIME format from the HTTP format so that you can generate test cases that have both?
Interesting question. Not right now, but that's a cool feature and I encourage you to create a PR for it.
Do we have one more question? Do we? No, I guess that's a wrap. Thank you so much, Alex.
Thank you.